Hey class, to start off the video today, we are going to watch a little clip from the movie Hidden Figures. So,
Paul, why are we still losing shingles off the heat shield?
We're working with a prototype of the capsule, Al. It's lit as 1/3 the size.
I get that. So, what do we do with our $1 million fan, Carl? Turn it down?
No, I don't think.
It was a joke. Paul, if the heat shield comes off, what do you think happens to our astronaut?
I know.
So we're gonna come up with a solve, right?
Yes, sir. We're working on it.
Ruth, what's the status on that computer?
She's right behind you, Mr. Harrison.
Does she handle analytic geometry?
Absolutely. And she speaks.
Yes, sir, I do.
Which one?
Both. Geometry and speaking.
Ruth, get me the... You think you can find me the Fernet frame for this data? Using the Gram-Schmidt...
Orthogonalization algorithm? Yes, sir. I prefer it over Euclidean coordinates.
Okay, good. Good, then I'm going to need it by the end of the day.
Yes.
And I'm also going to ask you to check Mr. Stafford's math as well as others on this floor from time to time.
I can handle that.
okay. So, what Mr. Harrison asks the computer to do was to use the data and find a frame given with the Gram-Schmidt orthogonalization process, and that's exactly what we're learning about today. I think it's cool that they got it into this movie. So let's get to our slides. Okay, so the big question is, if we have a subspace W, can we find an orthogonal basis for W? Often we have a basis, but it's not orthogonalized, and as we saw in the last couple sections, there's a lot of nice advantages if you have an orthogonal or an orthonormal basis. So if we don't have one, is there a way to get an orthogonal or an orthonormal basis? So that's what we're going to do. That's the process we're going to learn to do that. It's called the Gram-Schmidt orthogonalization. So just to start off with, as an example, we're just picking two vectors in R3 that aren't orthogonal. How can we change them so that they become orthogonal and that their span does not change? So we still want the orthogonal basis to be the basis of the same subspace. So this is the important geometry for the Gram-Schmidt orthogonalization. So here we have the vectors u and w, and we can keep one of the vectors. And what we want to do is then take the piece of the other vector that is perpendicular to the first. So we're going to keep u, and then what we do is we take the projection of w onto u, and so then we have this long vector here, which is the projection of w onto u, and we have w, and then we take the difference. And the difference, if we take w minus this projection, what we get is this vector right there. And that vector is orthogonal to u. So they draw it down here. Okay. So we break up the vector into or we find the part of w that goes in the direction of u, that's the projection, and we subtract that part off from w, and that gets us the perpendicular, the piece of w that is perpendicular to u. So that is that's the geometry of the Gram-Schmidt, and what we end up doing is we'll pick a vector, and then we'll take the second vector, project it onto u. We'd do this process, project it onto the first, and then subtract that projection off to get our second vector that's orthogonal. And then if we have another one, we project it onto both of those first two orthogonal ones, subtract both of those pieces off to get a third one, and then et cetera, et cetera. We can just keep doing that as many times as we want. So this is the algebra of the process I was just talking about. We can keep the first vector. So we've got a basis, x1 to xp. It's a subspace of W. They're not necessarily orthogonal to each other. Those vectors aren't. So we pick one, and then the way we build the next orthogonal vector is we take any other vector, and then we project it onto v1, which is x1. So these could say x1 or v1. They're the same vector, so it doesn't matter. We project it onto there, and we subtract it from x2. So that's exactly the geometry that we saw from up here. So we kept u, we project w on to u. So this is like our v1 now. U is now v1. This is x2. We project x2 onto v1, and then we subtract that off. So this is v1. Oops, sorry, this is x2 minus the projection of x2 onto v1 or onto u. So that's what we do. Now v2 is orthogonal to v1. And then we can take another vector, any other vector that's not x1 or x2, and now we take that third vector and we project it onto our first one, project it onto our second one. So now we've broken this down into, we have these two components of x3 that this goes in the direction of v1, this is how much x3 goes in the direction of v2. We subtract those off. The only thing that's left is the component of x3 that is that's perpendicular to v1 and v2. And we can just keep on doing that. So, and the span stays the same. All right, so here's an example with numbers. So here we have x1, x2, and x3. They span a certain subspace in R4. Let's find an orthogonal basis for W using the Gram-Schmidt process. And then find the orthonormal basis. So the Gram-Schmidt process will find an orthogonal basis, but then you have to go through and divide by the lengths of each of the vectors to turn it into an orthonormal basis. So they all have unit length. So x1, we take x1, let that equal v1. We can pick any of them to be that. So x1 is 1, 1, a negative 1, and 2. So here we get 1, 1, a negative 1, and 2. So now we are going to take x2, which is 1, 0, 0, a minus 1. So that's 1, 0, 0, a minus 1. So there's x2. And we're going to subtract off so x2, which is 1, 0, 0, 1 dot v1, which is 1, 1, minus 1, 2, because v1's right over here. So we're going to dot those together. What do we get? We get 1 plus 2, so we get 3. So this numerator is 3, and the denominator is v1 dot v1. v1 dot v1 is going to give us 1 plus 1 plus 1 plus 4. So that's going to give us 7. 4, 5, 6, 7. So the denominator is 7. So it's 3/7 times v1. So we're going to subtract off 3/7, 3/7, a negative 3/7, and I ran out of room, and 6/7. So if we subtract that off, then 1 minus 3/7 is oh, sorry, I'm not ice. I wrote it, yeah. This is x2, right? Yeah. So 1 minus 3/7. How come it gives us 8/7? I don't know. Where did I mess up here, folks? x2.v1, so that looks like it should be 3. So that's a 1, 0, 0, 2. So that's gives us 3, right? Okay, I found out my mistake. I didn't write down the negative here. So that's a -1, so that's not 3. That dot product will be a -1. Okay, so sorry about that. So the numerator here is a -1. So that means this whole thing just turning into a mess is, so it's a -1/7. This part is a -1/7, and multiply by v1. v1's up here, so I get a -1/7, a -1/7, 1/7, and a -2/7. And now we can do the arithmetic. So we're subtracting a -1/7, so that's adding 1/7. So 1 plus 1/7 is 8/7. 0 plus 1/7 is 1/7. 0 minus 1/7 is 1/7, and a -1 plus 2/7, because we're subtracting a -2/7 is a -5/7. Okay, there, we're good. So now we do a similar thing here, except we have to take the component of x3 and find out what the subtract off the piece that's going in the direction of v1, subtract off the piece that's going in the direction of v2, and what we have left will be perpendicular to both of those. So x3, well, so you do the same process that I did up here, just without making a mistake. So I'm not going to go through and walk through those. So normalizing this orthogonal basis gives an orthonormal basis. So these vectors here, this isn't a unit vector, this isn't a unit vector, this isn't a unit vector. So you have to find the length of each of those and then divide and make them unit vectors that way. So okay, so this is a new idea. This is a different way to factor down a matrix. So there's actually lots of different ways to factor down a matrix. We've already found one, the diagonalization theorem, that a square matrix, a lot of times, as long as the algebraic multiplicity and the geometric multiplicity match up for all eigenvalues, it can be factored down to p d p inverse. So that's one way to factor down a matrix. Let me fix my d there. So this is another way to factor it down. It's called QR factorization. Q is the popular way to write down, and it's like the popular representative for an orthogonal matrix. Okay, and R is going to be a triangular matrix. And this is not, you don't have to have a square matrix for this. This is for any m by n matrix. But the columns do have to be linearly independent. So you have to have n has to be greater than m or equal to. So because otherwise you'll be forced to have some dependent columns. So as long as we have that, then we can factor down as A into a product of two matrices, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A, and R is an n by n upper triangular invertible matrix with positive entries on its diagonal. So pretty strong. This is a pretty strong theorem. This is really, really nice. I'll show you one nice thing if we have time about that. So this is called the QR factorization of A. So this will always happen. As long as you've got an m by n matrix with linearly independent columns, you can find the Q and R so that Q is Q is an orthogonal matrix, so it has orthonormal columns, and R is an upper triangular matrix, and the diagonal entries are positive. The columns of the matrix Q can be obtained by performing the Gram-Schmidt algorithm on the columns of A and then normalizing them. And since the columns of Q are orthonormal, we know that QT times Q is the identity matrix, right? QT is Q transpose, Q inverse. Q transpose is Q inverse for orthogonal matrices. So what we're building up to is we know how to find Q. The question is, how do you find R? And if you do a little algebra, it turns out that once you find Q, R is easy. So that's what we're building up to here. Q takes a little work. We have to do the Gram-Schmidt algorithm and then normalize them. But since we can write it as QR, then so A is QR. So we're doing the algebra on this. So we're going to multiply both sides by Q transpose. So Q transpose A equals Q transpose QR, but this is just the identity matrix. So Q transpose A equals R. So this is our shortcut for finding R. See, that's what this side and that side. So once you find Q, you take the transpose, multiply it by A, and that is R. Slick. So really all the work is finding Q. I'll show you really quick one nice thing about this, and it's back to solving systems of equations. So if we're trying to find AX equals B, where these are vectors, then if you find the QR factorization for A, then you can write it as QR X bar equals B bar. And Q is an orthogonal matrix, so you can multiply on the left on both sides by Q transpose. So you get Q transpose QR X bar equals Q transpose B. And of course, everything on the left side, this goes to the identity matrix, the Q transpose Q. So you get R X Q transpose B. And you might think, well, how did that help out? Well, R is an upper triangular matrix. That's really, really nice if you're trying to solve equations. You're at the point where you can just back substitute since it's upper triangular. Like, it's really easy to solve when you have an upper triangular matrix. Or you can continue row reducing from there, but you've already done a lot of the work. So it does take... Sorry about that. It does take a bit of work to find Q, but with large matrices, it can be more efficient than doing all of the row reduction that you need. So, okay, so find the QR factorization of the matrix. These are the same three vectors we were dealing with before when we were practicing the Gram-Schmidt orthogonalization. So we can just go back, and Q will be those columns that we found before. We orthogonalized and normalized. So there's Q, and now to find R, we take Q transpose times A. So we would transpose this. So 1 over the square root of 91, 5 over the square root of 91, 8 over the square root of 91, 1 over the square root of 91, etc. Etc. So we take, this is Q transpose, and we're going to multiply it by A. And A was this matrix. So 1, 1, a minus 1, 2, 1, 0, 0, a minus 1. The last one is 0 and 3 ones. Okay, so now if we do this multiplication, you do end up with an upper triangular matrix, and it turns out to be this upper triangular matrix. So, so we're not going to go through and do that. Not the multiplication. We're not going to show if you go back and multiply Q times R, it does equal A. Okay, so find a QR factorization of the matrix. So I'm not going to take time and walk through this. It's the same idea that we've walked through so far, but you guys can go through. The notes are here. So what do you have to do first? Pick one vector to start with, and then use the Gram-Schmidt on the next one to find an orthogonal vector. So that's what they do here. They do the Gram-Schmidt, then they normalize. So you have to divide. So here you're dividing by the lengths. So you get those, and now you have Q, and then you can take the transpose, multiply by A, and you get R. So okay, that's it for this one. Thank you very much.